All right, so we're going to do some guided practice for the Test 5 review. I don't have my calculator next to me, so we're just going to go through the work being done, and calculating it is up to you. All right, so what is the kinetic energy of a 150 kilogram object that is moving with a speed of 15 meters per second? Okay, so we're looking for KE. Our KE equation is 1/2 mv squared. All right, we've got a mass of 150. You've got a speed of 15. Okay, so plugging and chugging, you'll get an answer. 2, an object has a kinetic energy of 25 joules and a mass of 34 kilograms. How fast is the object moving? Okay, so we know mass and we know kinetic energy. We are solving for velocity. Okay, so moving this thing around, we got to get the 1/2 over. So opposite of 1/2, multiplying by 2. So we got 2 KE. Getting the m over, it's being multiplied, so we would divide it over. So 2 KE over m, and then getting our squared off of there, we take the square root. Okay, so if you need to find speed and you've got kinetic energy information, it's just going to be the square root of 2 KE over m. Make sure that that square root is over the entire thing there. Following order of operations, that square root has to be the last thing you move over. Okay, so now 3, an object is moving with a speed of 35 meters per second and has a kinetic energy of 1500 joules. What is the mass of the object? Okay, so now we're looking for mass. Okay, so similarly, moving things around, getting our 1/2 over, that's 2 KE. Getting our velocity over, we're not looking for velocity here. We can leave that squared on, so our mass is just going to be 2 KE over v squared. Okay, 4. An object has a mass of 5 kilograms. The object is resting on the Earth's surface. How much gravitational potential energy does it have? Okay, so potential energy, gravitational, is mass times gravity times our height from the ground. Okay, so our height from the ground here, if we're sitting on the surface of the Earth, is 0. Okay, so h is 0. So it doesn't matter what mass and gravity are. For A, our gravitational energy is just 0. Okay, for B, the object is ranged to 50 meters from the ground. How much gravitational potential energy does it have? Okay, so now we do have a number for H. So B is not also going to be 0. We have done work to add potential energy. All right, you're going to be using mgh again, but this time H is 50, G, gravity, we're near Earth, so it's going to be 9.8, and our mass is going to be 5. Okay, so 5 times 9.8 times 50. Okay, C, if it were then dropped from 50 meters to the ground, what would its kinetic energy be at ground level? Okay, so we saw in A that at ground level, it has no gravitational energy. Okay, but at 50 feet, or at 50 meters, it does have gravitational energy. As it's falling down, it is losing gravitational potential. Okay, as it gets closer to the ground, it's going to be speeding up as well. Okay, so as you're losing gravitational energy, you are gaining kinetic energy. All right, so whatever amount of energy we had at B, that's how much total energy we have in the system, how much energy we added into it. So when we release it, it will be gaining that much kinetic energy because it's losing all of its gravitational. So whatever your answer was for B, that is your answer for C. Basically, if we want to look at a formula, our total mechanical energy equals our kinetic energy plus our gravitational energy. Our total mechanical energy is what we found in B. It wasn't moving at B, and it had some gravitational potential energy. Okay, so TME, that's just B. All right, and when it reaches the bottom, UG is going to be 0. Okay, so basically what we end up getting, UG goes away, your kinetic energy equals your total mechanical energy after it has fallen. Okay, so C will be the same as B. D, use the kinetic energy formula to find its speed after falling for 50 meters. All right, so we're going to be using this V equals square root of 2 KE over M again. That'll work perfectly fine. E, use kinematics to confirm your answer. Okay, so kinematics-wise, all right, thinking about this situation, we're looking for its speed as it reaches the ground. Okay, so we're looking for final speed. It's released from rest, so we know our initial speed. Can you not?
Natalie Link, please head to the buses.
Please do.
Natalie Link, please get on your bus at
Do
this
so
time.
quietly.
Thank you.
Wasting my time. Anyway, so E, we're looking for our kinematics. So you've got to know your final velocity. So final velocity needs to be in the formula. Our initial velocity is 0. We know the distance that it has fallen is 50 meters. And the thing that's making it fall is gravity. So we know our acceleration is 9.8. Okay? So we need a formula that doesn't have time in it because we don't know anything about time and it's also not asking for time. Okay? So that's going to be formula C. We've got VF squared equals VI squared plus 2ax. Okay, we're looking for VF, so getting that squared off of there, taking the square root, all that stuff. Okay, and the answer for these two should be the same unless you've made a mistake somewhere along the line. Okay, now number 5. A 5 kilogram object is raised to 50 meters above the ground on Mars. So that means we don't know what G is. It has 928 joules of potential gravitational energy. What is the gravitational acceleration on Mars? Okay, so we've got some information about gravitational potential energy. So UG equals mgh. Okay, it has given us a height, it has given us a mass, and this one is giving us our amount of energy. Okay, so if we're looking for G, we just got to solve for G. Should be pretty easy. Got some multiplication in there. We're just going to divide it over. All right, so when you're looking for your gravitational acceleration, it's going to be your gravitational potential energy divided by your mass and your height. Okay, there we go. 6, what is a scalar? Give 5 examples of scalars. So scalars are quantities that don't have direction. So a couple examples would be like time, right? You don't go seconds west. I mean, technically, seconds are also a measurement of distance, like if you're looking at latitude and longitude. So you could go seconds west, but that's not what we're talking about. We're talking about time, okay? So yeah, time does not have direction. Distance does not have direction, right? I tell you to go 5 meters, you could go in any direction. It's not prescribed by the value itself, okay? Speed, energy, all right? Anything that doesn't have direction is a scalar, okay? 7, a vector does have direction, has both magnitude and direction. So examples of that, instead of distance, displacement, because you're going a certain distance in a particular direction, from point A to point B in a straight line. Okay? Velocity has direction. Force, momentum, torque. All right? Anything that has direction is a vector. Okay? Number 8. Okay, so what angle produces the largest cross product? Where is a cross product 0? Okay, so an example of our cross product was when we were looking at torque. Right? Your torque is the cross product between R, your radius, and force. Okay, so written looking for the magnitude of that, it's R times F times the sine of the angle between them. Okay, so to get the largest cross product, all right, it's that angle that is determining whether or not we're going to get a large or small cross product out of here. Right? If we've got the same radius and force, the angle is the determining factor. Okay, so the sine, you get the largest value for sine when your angle is closest to 90 degrees or 270 degrees. Okay, so when sine is 90, that's when you're going to get your largest torque. You're going to get your smallest torque, you're going to get 0 torque when your angle is 0 degrees or 180 degrees. Think about trying to rotate a wrench. All right, if the wrench is pointed along here, if I grab the handle and push up, I'm pushing it 90 degrees, okay? I'm producing the largest torque. But if the wrench is pointed that way still, and I'm just pushing in that direction, it's not going to turn the bolt because I'm not applying a force that's actually making it rotate. I'm applying a force just jamming a wrench into a bolt. That's not going to do anything. Going 180 degrees is even less useful because now I'm pulling the wrench off of the bolt. It's not going to move anywhere if there's no wrench on it. Okay, so 0 and 180 degrees, the sine of 0 and 180 is 0. Okay, so you get your largest values at 90 degrees, you get your smallest values at 0 and 180. All right, the next one, number 9, a cross product is the opposite. Okay, so work is the cross product between force and distance. Okay, written looking for the magnitude, Fx cosine theta. Okay, so if the force and the distance are the same, it's dependent on the angle. Okay, with cosine, you get your largest values when your angle is closest to 0. Okay, if I want to push something over a particular distance, it's going to be most efficient to push it in the direction it's moving. When theta is 0, I will do my most useful work. Okay, if I'm trying to move something to the right and I'm applying a force that's just upward, it's not going to move that way. Okay, I'm not going to get it to do work to the right if I'm applying a force where none of it is pointed to the right. Okay, so that's at 90 degrees. You end up with your smallest dot product when the angle is 90 degrees. You get your largest dot product when the angle is 0 or 180. Okay, so now next one, 10. How much work is done on an 8 kilogram object moving at 10 meters with an acceleration of 6 meters per second squared? Okay, so we're looking for work. Work, as we just mentioned, is force times your distance times the cosine of the angle between them. Now, this one is not telling us a direction. All right, when you're looking at a dot product like this one, you assume that that angle is 0 degrees. You assume that you're applying a force in the direction you want it to move. Okay, so angle is 0. Cosine is 0. That's just going to turn into 1. Your force, okay, it's not flat out telling us a force. What it does tell us is that we've got a mass of 8 kilograms and it is accelerating at 6 meters per second squared. Shut up. So if we've got mass and acceleration, you can just use Newton's second law there. Okay, our mass of 8 times our acceleration of 6, that's going to get us our force. Multiply that by your distance of 10, and there's your work. Okay, number 11, if a force of 100 newtons is applied at 60 degrees above the horizontal on an object, forcing it to move 20 meters, how much work is done? Okay, so again, you're using this work equals force times distance times the cosine of the angle. It's just in this one, the angle is not 0 degrees. It is specifying that we're specifically looking at 60 degrees. Okay, so that theta there is going to be 60. Okay, the rest of it plugging and chugging. 12a. Find the missing variables magnitude and direction. Okay, so this one, we've got a radius and we've got a force. We're looking for torque. Okay, so torque is RF sine theta. Okay, and we've got R, we've got F. The angle between these two, 90 degrees. Okay, so that means that sine theta isn't something we're going to have to worry about. In fact, we don't need to worry about it in any of those four. They're all at 90 degrees to each other. We just need to worry about what the product of those two is. So 1 times 5, you got 5 Newton meters of torque. All right, but when you're worrying about torque, you do have to use right-hand rule to find your direction. Okay, so remember with right-hand rule, your first vector, your radius, is your pointer finger. Your second vector, your force, is your middle finger. And your third vector, the cross product of the two, is your thumb. All right, pointer finger always going straight forward. Your middle finger can move in case you're looking at angles other than 90 degrees. Okay, but keep your thumb pointed directly up, your pointer finger pointed directly forward. All right, so if we're looking at this one, I'm going to have to turn the page just to actually let my wrist go into that position. So I've got my radius pointed towards the bottom of the page. I've got my force pointed towards the right side of the page, and I've got my thumb pointing out of the page towards the camera. Okay, so that means that the torque that you find there is going to be 5 Newton meters out. Okay, for B, we're now missing the force. Okay, so solving this thing for force, that's just going to be your torque divided by r sine theta. That equals force. And again, you're at 90 degrees, so that sine theta doesn't even matter. It's just going to be your torque divided by your radius. So that'll be 1 divided by 15. So now finding the direction there, remembering our torque is our thumb. So torque is coming outward. Our radius is going towards the left. So my force is going downward. All right, so torque down. Sorry, force down, my bad. C. All right, we are missing our torque. No, sorry, we have our torque, we have our force, we're missing our radius. So solving this thing for radius, we instead end up getting torque divided by force times the sine of our angle. Again, 90 degrees. You don't need to worry about sine theta. It's just torque divided by force. So 3 divided by 10, 0.3. So now looking for our radius. All right. My torque is pointed towards the left side of the page. My force is pointed towards the bottom of the page. My pointer finger, my radius, the thing I'm looking for, is pointed into the table. All right. So this one is going in. My direction is in. Remember when you're drawing the diagrams of them, out of the page is just a dot, like you're seeing the tip of an arrow coming towards you. All right, you can't see the whole arrow behind it because of parallax and stuff. It's just coming directly at you. If it's leaving, you will see the feathers at the back side. All right, so coming out of the page is a dot, going into the page is an X. All right, D. We've got force, we've got radius, so now we're looking for torque. So going back to that original equation, RF sine theta, our force is pointed towards the left-hand side. Our radius is pointed into the page. My thumb is pointed up. Okay, so RF sine theta, and whatever number it gives you, it's going upwards. All right, so that'll do it for number 12. Number 13, The light's off. That's okay. I opened the window, planned ahead. Look at me go. 13, a bolt connecting the main and rear frame of a mountain bike requires a torque of 15 newton meters to tighten. If you're capable of applying 40 newtons of force to a wrench in any given direction, what is the minimum length of the wrench? All right, so we're looking for R here, and it's asking for the minimum length of the wrench. Basically what that's saying is we're applying this force in the optimal direction. What that means is that theta is 90 degrees. Okay, so we've got a torque, you've got a force, and you're looking for the minimum radius. So you're going to be using this, right? It gave you torque, it gave you force, sine of 90. So it'll just be 15 divided by 40. That'll get you your answer. Number 14. Is this the last one? It is. Look at us go. Number 14, we've got this little pivot point, and we've got a rod with some masses hanging on it. So two masses are hung from a rod. What distance is the 0.6 kilogram mass from the pivot point? Okay, so if we're looking at our pivot point, we don't have a distance here. We need to find that. We're looking for that. Okay, if this thing isn't moving, that means that the torque being applied by this 0.35 kilogram mass is equal and opposite to the torque being applied by the 0.6 kilogram one. All right, think about the direction it's trying to rotate. This one is trying to turn it counterclockwise. This one is trying to turn it clockwise. All right, and they've canceled out. Okay, so if we can find this one's torque, that'll tell us the other one's torque. Okay, so thinking about this one's torque, we've got a distance. That's good. We've got radius. All right, and we've got a mass here of 0.35. Okay, so the force that's being applied by this is a downward force equal to the weight of that mass. Okay, and if we're looking at our angle here, our radius going directly to the right, our force going directly down, that's a 90-degree angle. Okay, so we're looking for the torque there. All right, looking for torque, you've got RF sine theta. All right, we've got our mass here, so we probably want to find our weight. In reality, gravity ends up getting divided back away later, so technically we could do this with just the mass, but you know, just in case later on down the road you're dealing with some weights and you're using mass instead, that might cause some problems. So we might as well find that force there. All right, so the force being applied is the weight of that object, which will just be mass times gravity. All right, so that 0.35 times 9.8, that'll get you your force, and then multiplying that by 0.3 to get it in meters, that'll give you your torque in Newton meters. All right, whatever torque you end up getting here is equal to the torque applied by this one. Okay, so find that torque first. Take your radius, 0.3, multiply by mass times gravity, and sine of 90, and there's your torque. Same torque there. Okay, so using that torque, we're now looking for radius, which means we're going back to this formula. All right, so take that torque and divide by force times sine of theta, but for this one. Okay, so again, you're going to have to do the mass here times 9.8. So 0.6 times 9.8, dividing that away from the torque that you found earlier. All right, so step by step, find the torque of this one. That is the torque of this one. Use that torque to find the radius. Okay, and that does it. How about that? Look at us go. Okay, so if you have any additional questions, let me know, hopefully before the test. See ya.